Hi, welcome back. We're looking at example 3 in 6.3 Pascal's triangle and expanding binomial powers. In this example, we're going to relate other patterns to Pascal's triangle. So the diagrams represent the triangular numbers. So part A, it says write the number of dots in each sequence or in each diagram as a sequence. So we have those four numbers here. So let's go ahead. We'll start with that. We have 1, 3, and the next one is 6. And then the next one we have 4 and 3 is 7, plus 3 is 10. Okay, part B says locate these numbers in Pascal's triangle, describe their position. So let's just write out the triangle one more time. So we're looking for this sequence, and it could be found here. It can also be found there. Okay, notice there is always symmetry in the triangle. So how could we describe this? Well, this is located in diagonal 2. All right, and then the next part says write an explicit formula. So this is going to have the form T of n equals and something with n in it. And then a recursion formula, that's where we're going to say that any term is equal to the previous term, and then we do something with it. So it wants us to do that for the triangular numbers. So could we come up with an explicit and recursion formula for that sequence? So let's begin with the explicit formula. So I'm going to set this up like a table of values. So we'll say the term number, which will be represented by n. And then we have the value of the term, which we'll write as f of n. We'll put it in function notation. Okay, then we're going to do our first differences and we'll see what happens. So term 1, 2, 3, and 4. So our term values was 1, 3, 6, and 10. Those are the numbers from the sequence. Taking our finite differences, we would have 2, 3, and 4. Those are nice numbers. Taking the seconds difference, it's pretty obvious. We get 1 and 1. So our explicit formula is going to take on this form. So because the common difference shows up in the second column, it is quadratic. So I'm going to write out an explicit formula and like standard notation. So the standard form of a quadratic. So we'll write it as n squared plus b n plus c. And the rule is when this is quadratic like this, the letter a right here is always going to be half of this value. So we're going to say a equals a half times 1. So whatever number is constant that goes in this bracket, just take half of it. That's always going to be the leading coefficient for our quadratic function. So we can actually begin this out by writing f of n equals a half n squared plus b of n plus c. So in order to get the explicit formula, we just need b and c now. So there's a couple ways we can do this. We can substitute in some known points that we have, or like ordered pairs. So why don't we do that? Sub 1, 1. So this means f of 1 is going to equal half 1 squared plus b times 1 plus c. So f of 1 is actually 1. That's the y value. So we'll have 1 equals half times 1 squared is a half plus b plus c. Subtract the half on both sides. So we have a half equals b plus c. I would call this equation A. Now we're going to get a second equation. So to do that, we'll take our next order pair and sub that in. So that was 2, 3. So f of 2 is going to equal a half 2 squared plus b times 2 plus c. F of 2 is 3. Half of 4 is 2. Subtract 2 on both sides. We have 1 equals 2b plus c. Call this equation B. So what we can do is just maybe do substitution. We could also do elimination. We're just trying to solve for our variables b and c. Once we get b and c, we'll plug them into here and here, and that'll give us our explicit formula. So this is really easy. Why don't we isolate for c in part A? Okay, so we're going to isolate for this letter and this equation right here. So c is going to be a half minus b. Okay, just bring the b to the other side, right? Now we're going to sub c equals a half minus b into equation b. So we always, whatever we isolate for, we always sub into the other equation. So it's going to go right into here. 1 equals 2b plus half minus b. So we can see here that 2b minus b, those will cancel out to just 1b. So we're going to have 1 equals b plus a half. So therefore b equals a half. Just going to highlight this, because we'll come back to that later. And now we're going to sub b equal to half. Sub it into any equation we want. We might as well plug it into right here, and we can solve for c. And we get 0. Okay, so we just found our values for b and c. So we can go ahead and we can plug those in up here. Sorry, not that one. This one right here. Okay, so our final equation, we're going to have a half n squared. B is a half, so we'll have plus a half n. And then c is 0, right? So we don't need to write anything for that. I'm just going to highlight this one in green. And this is our explicit formula. Okay, explicit is always a little bit more challenging to get than the recursion formula. So we'll do that one next right now. So the recursion formula. Okay, remember we just need to look at this pattern and we need to say, okay, what do we need to do to go from here to here? And then what do we need to do to go from there to there? So we're always using the previous term to get the next. So sometimes it's helpful to write them out. So f of 1 equals 1, f of 2 equals 3, f of 3 equals 6. So, and I also, what I do is I even write them out in terms of the previous one. So we could say f of 2 is actually equal to f of 1 plus 2, okay, in order to get 3. And then f of 3 is actually equal to f of 2 plus 3. And then f of 4 is equal to f of 3 plus 4, right? So to get 10, we take 6 and we add 4, right? That's what that says. So this is real easy because I can really see the recursion formula here. So any term, f of n, it's going to be the one previous plus n. Notice how the numbers here always line up with the term number that we're looking for. So, like I said, that was much simpler than the explicit one. Okay, that's it for this example. I'll see you guys in the next video, which will be our last example.